All right, so let's get started on our new chapter. We got a new set of functional groups here. This chapter focuses on ketones and aldehydes. And we've talked about aldehydes and ketones before, but never really as like the focus of our lectures. They've just kind of been either reactants or products in lectures that we've learned. So first of all, these are both functional groups that contain that carbonyl bond. All right. The first thing is let's make sure that we can distinguish between aldehydes and ketones. So I'm going to put down a few molecules, and you're going to tell me if you're looking at an aldehyde or a ketone. That's fine. We'll do those four. All right, so the key distinction between aldehydes and ketones is just where that carbonyl bond is located. If it's located on a terminal carbon at the end of a molecule, it's considered an aldehyde. And if it's located in the middle of a molecule, it's considered a ketone. All right, more strictly put, if we zoom in on this aldehyde here, how many bonds are explicitly drawn on this carbonyl carbon? We got 1 plus 2 plus 3, right? So then how many hydrogens are there on that carbonyl carbon? 1, right? I got 3 bonds, so this last one has to be a hydrogen. So that's the feature of an aldehyde, is that carbonyl carbon is bound to a hydrogen, as opposed to a ketone. There's no hydrogens on that carbonyl carbon. All right, it's got 1, 2, 3, 4 carbon bond. Well, I guess 2 carbon-oxygen bonds and then 2 carbon-carbon bonds. Right? So aldehydes have hydrogen on their carbonyl carbon. All right, so then these last two, take a second if you, based on what we just discussed, tell me what these two are. All right. This one here. What do you think? Who thinks it's an aldehyde? Raise your hand. Yeah, it's an aldehyde. Cool. Right, if we look at this carbonyl carbon, it only has these 1, 2, 3 bonds. There's got to be a hydrogen sticking off of there. And then this one, my carbonyl carbon has no hydrogens, right? Those are both carbons, so this is a ketone. All right, so both aldehydes and ketones both possess that carbonyl bond. The difference is where they're located. Again, in an aldehyde, they're located on a terminal carbon, and in a ketone, they're like in the middle of a molecule. Aldehydes and ketones, it kind of drives me nuts that they're considered to be two separate functional groups. They behave basically the exact same. Because they're two separate functional groups, we're going to have different ways of naming them, okay? But in terms of like, oftentimes the logic in organic chemistry is to divide things up into functional groups because different functional groups react different ways. We're very much going to group aldehydes and ketones together when we talk about their reactions. If I had to guess, it would be historical sugars contain either aldehydes or ketone functional groups. Huge amount of effort was put in, 100 years ago, just figuring out all the different sugars in the human body. And I imagine that's why these two got separated into different camps. But again, for us, we're always going to be talking about them sort of together in terms of their reactions. All right, nomenclature will be our focus for today because that's where we're going to start with our new functional group. How do we name it? All right, so first one we'll do is ketones. All right, and let's just look at an example here. So 5-carbon alkane, whoa, voice crack. Alkane would be pentane. If we throw a ketone functional group on there, this becomes pentanone. Oops. That O-N-E functional group for a ketone. All right, so ketones have an O-N-E suffix. Okay, much like we've seen with other functional groups, we also have to indicate the location of the functional group in our name. So this isn't just pentanone, but rather 1, 2, 3, 3 pentanone. Okay, so same game that we've played before, we just have a different suffix for ketones, that O-N-E ending. All right, so let's just do a couple. Oh, whoops. right, so I'm going to find my parent chain. 1, 2, 3, 4, 5, 6 carbons. Okay, I'm going to number my parent chain. 1, 2, 3, 4, 5, 6. Go the other way. 1, 2, 3, 4, 5, 6. So which numbering scheme am I going to pick, red or blue? Blue, right? Pick the lowest number on our functional group. So this would be 3 hexanone. All right, just like we saw before, the E of pentane gets replaced with that new functional group, the -one ending. So hexanone. All right, for this next one, we got to find our parent chain, our longest continuous set of carbons. That'll be those 5 there. Again, I'm going to number 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I skipped a step. Let's name our group right here. This 1 carbon group would be a methyl group. Okay. So when I put my name together, I'm going to make sure to, we've seen this before, we're going to prioritize that functional group. In this case, it actually, the methyl would be on 3 no matter what, but it is important that we prioritize that ketone functional group. So this would be 3 methyl, methyl 2 pentanone. All right, and again, find our parent chain. 1, 2, 3, 4. Again, we can number it both ways. Okay, and I guess here's a better example where we're going to completely ignore this chloro group here. All right, that's what this thing would be a chloro group. But when we pick our numbering scheme, we're only going to pay attention to our functional group, or rather our ketone functional group. So this would be, so we're going to go with the blue numbering scheme. So this would be 3 chloro 2 butanone. Because it's 4 carbons. 4 carbons is a bute. Okay. So everybody, I want you to take a second and try to draw me the simplest ketone that you can. By simplest, I mean the fewest number of carbons. All right, try to think of the smallest ketone that we could have. All right, so if I have a ketone, it's got to have that carbonyl bond, right? But then to be a ketone, remember, this can't have any hydrogens here. So I'm going to have a carbon on one side and the other side. So the smallest ketone that you can get is actually 3 carbons. Okay? And this molecule here, just for historical reasons, has a, you would expect this to be something like 2-propanone. Nobody calls it that. Nobody would have any idea what you're talking about, all right? Because this has a common name that is way more commonly used, and that is acetone. You may have heard of acetone before. It is the active ingredient in most nail polish removers. It is a great organic solvent. It's used all the time. In an organic chemistry lab, it's just used to wash glassware. All right, it's just a super commonly used solvent, and for historical reasons, nobody calls it by its real formal name. It goes by its nickname, acetone. Okay, so this is one that we just kind of got to know has a special name. All right, so now we're going to go on and talk about nomenclature of aldehydes. Okay. And again, let's just look at an example. Again, if this is pentane with 5 carbons, we're going to replace that E with our new ending, all right, which for an aldehyde is Al. So this is pentanal. So for aldehydes, we use this Al suffix. All right. What's the location of this functional group in my molecule? Which is what carbon number? 1, right? I'm going to start numbering from over here because I want that to be my lowest possible number. Okay? So now let's think. If I pick it up and I'm going to pick up this functional group and I'm going to move it here, is that an aldehyde? No, right? That's no longer an aldehyde. What if I move it all the way to the other end of the molecule? Yes. That's an aldehyde. But what's my numbering scheme going to be? Still the 1. It's still 1, right? No matter which carbon I put that on, whatever endpoint I put it on, that's just going to be what carbon 1 is. So because of that, with aldehydes, we have one more sort of weird rule here, which is we're not going to number, I guess do not number, the aldehyde functional group. Okay? Instead, we're going to just assume, we always assume that it's on carbon 1. Okay, so aldehydes, because they're like necessarily on one of those terminal carbons, and whatever terminal carbon we put it on, we're just going to start numbering there. We always just assume that it's on carbon 1, and we don't bother building that into the name. Okay, so let's do a few examples. so 1, 2, 3, 4 carbons. That would make this a butanal. And we're not going to bother putting 1 butanal because there's no such thing as 2 butanal or 3 butanal or anything else, right? If it's a butanal, you know that that carbonyl group is on that end terminal carbon. All right. Again, we need to find our parent chain, and this is a good example to remind ourselves of that rule that the parent chain must contain our functional group. So yes, we're looking for the longest continuous set of carbons, and you may be tempted to say that it's these here, but that doesn't include that aldehyde functional group, right? So we want the longest continuous set that includes that functional group. Okay, so that makes this 2-carbon branch point right here an ethyl group. All right. We need to remember with aldehydes that even though we don't put the number in the name, that's just because we always assume that carbonyl carbon is carbon 1, right? So when I'm numbering my parent chain, I need to start with that carbonyl carbon as carbon 1. So this would be 2-ethyl, but again, not going to bother to put the location of that carbonyl group. So just hexanal. All run together, right? We only place that we include dashes is to separate numbers from letters. So since I'm just running 2 letters together, I'm not going to stick anything in the middle here. Just ethyl hexanal, 2-ethyl hexanal. All right, and again, for this one, we're going to find our parent chain. Okay, I have these 2 halogen functional groups here, a chloro group and a bromo group. Okay, I'm going to start numbering, and which is going to be carbon 1? That carbonyl carbon, right? So remember, this is a good example where you might be tempted to go from over here because that puts those at a lower number. But we have to remember that that carbonyl group, carbonyl carbon, is going to be the carbon number 1. Okay. And I have these 2 groups, a chloro group and a bromo group, which is going to come first when I start sticking my name together. The bromo, right? Remember when we're assembling, we're going to put them in alphabetical order, our substituents. So 5 bromo, 6 chloro, heptanal. Hept, because hept is for 7 carbons. Okay. All right, so now let's just mix them up here, put them all together. All right, I'm going to put down a few molecules. You're going to give me the name of these molecules. so first one, got to find that parent chain. And this one, it's a little tricky because of this little kink here. Remember, we want the longest continuous set of carbons. It's got to contain this functional group here, but it still needs to be the longest. So it's actually going to be these 7 carbons here that are my parent chain. So this 2-carbon branch point right here would be an ethyl group. I want that carbonyl bond to have the lowest possible number, so I'm going to start numbering from this direction here. So we got a 7-carbon parent chain. My ethyl group is on carbon 4, so 4-ethyl. And then this is a ketone, right? Not an aldehyde, so I still have to put the location of that ketone functional group. So 2-heptanone. O-N-E for that ketone functional group. I guess that's kind of the first thing that we should have done. Is this an aldehyde or a ketone? It's a ketone. So that's going to let us know how we go about naming that. All right, this looks really weird, right? How many carbons are there in this molecule? Just that one, right? How many hydrogens are there? 2. I got to have 4 bonds total for that carbon. So if I were to sort of draw out the Lewis structure here, including all my carbons and hydrogens, that would be this molecule here. This is the simplest aldehyde that you can have, right? So this is an aldehyde because I have that hydrogen on my carbonyl carbon. All right, so 1 carbon would be meth. So methanal. All right, this also has a common name that you may have heard of that's more widely used, which is formaldehyde. Famously used to preserve dead bodies and stuff like that. So if you have ever been in a biology class where you did any dissection, you'd be familiar with the smell of formaldehyde, which is really pungent, okay? I would accept either one of these. Truthfully, formaldehyde is more commonly used, but methanol you may hear. Unlike, just to be clear, unlike this example here, I'm not going to give it to you if you tell me 2-propanone. You have to know that this is acetone. Okay? For the other one, I would accept either of the common name, either the common name or the methanol, the formal name. All right, so here do we have an aldehyde or a ketone? Aldehyde. So I still got to find my parent chain. Cool. That carbonyl carbon of my aldehyde has to be carbon 1, so I'm going to start numbering from there. Okay, I guess we got 5 total. We can make a note. 2, 3, 4, 5. We got these 2 bromo groups. All right, so when I put my name together, I'm going to go 3,3-dibromo. All right, a very common mistake when doing nomenclature. They got 2 groups on the same carbon, so you're really tempted to give me one position, right? 3-dibromo. You got to include the location of both of them, right? So 3,3-dibromopentanal. All right, so don't forget the location of both. And then this one here, what's my parent chain? Yeah, excellent. Cyclohexa something, right? Cyclohex. And since this is a ketone, hexanone. All right, and as we've seen with other cyclohexa whatevers, cyclohexanol, for example, we don't bother writing one cyclohexanone, because if I pick up this functional group and move it, now that's carbon 1. Move it over here, now that's carbon 1, right? So wherever I move it, it's going to be one cyclohexanone, so we just say cyclohexanone. Okay, we don't have to put the location. No, yeah, no, right? Because on either side is necessarily going to be another carbon if it's on a ring like that. Yep. Yeah, there's no cyclohexanal. You can't have it. All right, so next class we'll sort of dive into reactions, but let's just take, since we have some time, let's take a minute to remind ourselves. The first place that we saw aldehydes and ketones was oxidation of alcohols. Okay, so this was the first place where we saw these, so let's just remind ourselves. If we take a primary alcohol, we can oxidize that. All right, everybody take a second and give me what my product would be. What's the functional group on that product? Aldehyde or ketone? Aldehyde, right? Primary alcohol means that hydroxyl group is sticking out on an end carbon, right? So we'll get an aldehyde out of that. And these can be further oxidized to a carboxylic acid. So remember, if you want to do this one step here, you need to use a weak oxidizer, and we had 2-DMP or the PCC, the two 3-letter abbreviation ones. Okay, if we have a secondary alcohol, weak ox. I was being lazy. A secondary alcohol would be oxidized to what? What functional group? Aldehyde or ketone? Ketone, right? Since it's in the middle, we would get a ketone from a secondary alcohol. All right, and can I oxidize this any further? No. All right, so it's kind of stuck there. And because of that, we can either use a weak or strong oxidizer. All right, and the strong was that sodium dichromate business. All right, and then what about a tertiary alcohol? It does not oxidize, exactly. Tertiary. If we tried to oxidize that, regardless of what we use, it's not going to work. So, first time that we ever introduced this concept of aldehydes and ketones, they were of the products of these oxidation reactions. So remember, if we're starting with an alcohol, we know how to get ourselves to either an aldehyde or ketone using one of these oxidation steps. We have to use a weak oxidizer for a primary alcohol. Secondary doesn't really matter. We can use whatever we have on hand. Okay? But that would get us to our aldehyde or ketone functional group, which is again the focus of this chapter. All right, so you're going to be done there. We'll pick up on reactions of aldehydes and ketones next time.